Way to go, Bumbo! You need to use more force to get your cap back.
You used the word force. But do you know what the word force really means?
Well,
the word force is used in a variety of situations in common parlance. However, in science, force is what acts on a body to make it move or stop it from moving. In this lesson, you will learn about force, its effects and its characteristics. At the end of this lesson, you will be able to define force, illustrate the effects of force, list the characteristics of force, distinguish between balanced and unbalanced forces, and explain friction. To explain the concept of force, let's first observe some real-life situations. What do you think these people are trying to do?
they're trying to perform some tasks requiring force.
That's right. As you can see, the first task involves force in kicking a ball and setting it in motion. The second requires force to roll a boulder off the cliff. In the third, force is being applied to try and stop a moving bus. Thus, if we use these examples to define force, force is an agent that tries successfully or unsuccessfully to move a body which is at rest or to stop a moving body. Let's go back to Bumbo and Jumbo and their clown act in the circus. Bumbo applies force on Jumbo, trying to push him away so that he can retrieve his cap. Initially, Bumbo does not succeed, even though he's trying hard and exerting force.
I guess he needs to push harder.
That's right. When Bumbo increases the force exerted on Jumbo, he is able to push Jumbo away.
There you go. He got his cap.
This child is applying force, trying to stop the dog from breaking free of the leash. If you have ever taken a dog for a walk, you have probably had a similar experience. A dog that is eager to get away can apply a considerable amount of force on the leash. You can say that a force is being exerted on the bodies in both these cases.
Oh. So here two forces are combined. Looks like force affects our life in a lot of ways.
True, although you can't see, taste or touch force. We all feel the effects of force. A force acting on a body can change its state of rest or of motion, its direction of motion, or its shape. Let's look at each aspect of change induced by force, one by one. In our initial example, the force applied by Bumbo made Jumbo move. Similarly, a push to a stationary shopping cart sets it in motion. A child uses force to pull a box of toys on the floor. A football goalkeeper applies force on a fast-rolling ball to stop it and save a goal. In all these cases, the state of rest or of motion of an object is changed. On a hockey field, when the ball is passed from one player to another towards the goal, players use their hockey sticks to guide the ball. Do you notice that as the ball is guided with a hockey stick, it often changes its direction of motion? This change in direction is also a result of the force applied on the ball through the stick.
And how does force affect the shape of an object?
You may have noticed how a balloon man creates figures from balloons?
Yes. They do that by squeezing the balloons in different places on the balloon.
Right. By squeezing, they are applying force on the balloon. This makes the balloon expand in other areas. You can also observe this effect in a rubber band, a kitchen sponge, or a beanbag chair. A rubber band expands on pulling, while a sponge contracts on squeezing. Beanbags are popular because they take different shapes depending on the position of the person sitting on them.
So how do we identify force?
You identify force using its 4 characteristics: magnitude, line of action, nature, and point of application. Magnitude is the measure or quantity of a force. Magnitude of force is quantified in Newton in the SI system and in dyne in the CGS system. Look at Bambo trying to push the 2 wooden blocks of different sizes towards the wall. He had no problems pushing the smaller block, but he seems to be struggling with the larger block. There, he's done it. What do you think was the difference in these 2 cases?
He had to apply more force to move the second block.
Correct. The magnitude of the force required to move each of the 2 blocks was different. The magnitude of force is indicated by the numerical value depicting the quantity of force applied and the unit of the force. Line of action is a line along which the force acts. Consider a book kept on a table. Do you think it exerts any force on the surface of the table? Doesn't look like it, does it? In fact, its weight acts as a force downwards on the table. You can say that the line of action of force is downwards. However, if you try to push the book, you need to apply force horizontally. Therefore, the line of action of the force applied on the book will be horizontal.
So, the line of action can be horizontal or vertical.
Not just horizontal or vertical. Line of action can also be inclined. For example, when a golfer hits a ball, he applies force at an angle from a horizontal surface. Hence, the line of action in this case is inclined. A force can be a push or pull force by nature. For example, a cue pushes the billiard balls forward, while a truck pulls a trailer behind it. Finally, let's look at the point of application of a force. The effect of force on a body depends on the point at which the force is applied. To understand what this means, consider the scenario where a clown in a circus is pushing another clown. When the clown is given a push on his upper body,
Oops! He fell face down.
Now, what if the point of applying the push is changed? A push on the middle of his body, for instance. Did you notice the clown didn't fall at all? He simply moved ahead. Now let's see what happens when the push is directed towards his lower body. The clown loses balance again, and this time he falls on his back. So, based on the characteristics of force, can you determine whether it is a scalar or a vector quantity?
Let's see. A force requires a magnitude as well as a direction, right? This makes force a vector.
Very good. Let's move on to learn more about types of forces.
Wow! They all seem to be applying a lot of force, but nothing is happening. How do you explain that?
So far, you have seen effects of single forces in terms of pulling and pushing. But in real life, there are often multiple forces acting on a body simultaneously. For example, in this case, there are an equal number of people on both sides. So, the force applied on one side of the rope is being counteracted by the force applied by the other side of the rope. That is, the force on both sides is balanced.
Does that mean there will be no movement if forces are balanced?
That's right. In such cases, because force is a vector, we must consider the result of the multiple forces acting on the body. This resultant force is called the net force. Net force is the sum of all the forces acting on the body. The magnitude and direction of the net force on the body depends on the magnitudes of the individual forces and their directions. If two forces, Fa and Fb, act in the same direction on a body, then the net force, Fa plus Fb, acts in that direction. In the same setup, if Fa acts in the direction opposite to Fb, and Fb is greater than Fa, then the net force becomes Fb minus Fa, and acts in the direction of force with a greater magnitude, that is, Fb. In case of multiple forces acting on a body, when the net force is zero, the forces are known as balanced forces. For example, this game of tug-of-war.
Doesn't look like this game is going to end. Neither of the teams seem to be making any progress.
Yes, this game will have to be a draw, unless we do something to tip the balance of the force. Let's see what happens if we add a person on one of the teams. See, the team with more people won. That's because adding another person made the forces on both sides unequal, and the net force was no longer zero. In such a case, the forces are said to be unbalanced. The concept of balanced and unbalanced forces applies to objects at rest as well as moving objects. When forces are balanced, a stationary object remains at rest and a moving object continues to move at the same speed and in the same direction. When forces are unbalanced, the object may change its state from rest to motion or vice versa, or change its speed or direction of motion in the direction of the net force. Let's observe this game of cricket. As you can see, the ball, when hit by the batsman, slows down and stops after rolling a certain distance. Do you see any force being applied to stop the ball?
No. Ideally, the ball shouldn't stop, right? No one applied any force to stop it.
The ball stopped due to a force called friction. Friction is the force resisting the relative motion of two bodies that acts along the surfaces it contacts. The bat hits the ball with a certain force that makes the ball move ahead. When the ball rolls down the field, friction acts in the direction opposite to the direction of the motion of the ball. Gradually, the frictional force overcomes the force that made the ball move, slowing down and eventually stopping the ball.
Is friction the same on all surfaces?
That's a good question. Look at this.
It needed a lot of force to push the block in the first case.
And yet, in both the cases, it is the same block.
So was it the type of surface that made the difference?
Yes. Rough surfaces offer more friction, while smooth surfaces offer minimal friction. That's why, when you try pushing a wooden block kept on a rough surface, you need to apply a relatively large amount of force to move it. Conversely, if you push the same block on a slab of ice, it moves relatively fast. you find friction at work almost everywhere around you. Some examples are objects lying on a slightly inclined plane, pens, pencils, and chalk in use, automotive brakes, and foes between vehicle tires and the road when in motion. This brings us to the end of this lesson on foes. In this lesson, you have learned about effects of foes, characteristics of foes, balanced and unbalanced forces, and friction. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Let us take a look at a billiard table, something most of us are all familiar with. The balls are all stationary. What will make them move? A push from the stick, that is, an external force. The important thing to note here is that without this push or an external force, the balls will remain at rest for an infinite duration. Thus, motion is a direct result of force. This relationship between force and motion was studied by Galileo and Newton. Galileo was the first to abstract from what he and everyone else saw. An object in a state of motion possesses an inertia that causes it to remain in that state of motion unless an external force acts on it. Sir Isaac Newton further studied Galileo's ideas on force and motion and presented three fundamental laws that govern the motion of objects. These three laws are known as Newton's laws of motion. In this lesson, you will learn about Newton's first law of motion and inertia. At the end of this lesson, you will be able to explain Newton's first law of motion, explain the concept of inertia, examine inertia based on object size. Newton's first law of motion states that an object will remain at rest or continue to move at a constant speed in a specified direction unless an external force acts upon it. This law relates force applied on a body to the change in its velocity. There are two aspects of this law that we need to consider. First, an object at rest will remain at rest unless an external force is applied to it. All objects at rest conform to this. For example, on a golf course, a ball on a tee remains at rest until the golfer hits it. When the ball is hit, a force is applied setting the ball in motion. The second aspect relates to a moving object. An object in motion will move at a constant speed and in a fixed direction, unless an external force is applied on it. Consider an artificial satellite revolving around the Earth. It moves with a constant speed and in a fixed orbit. The orbit of satellite will not change on its own. In case the satellite is required to change its orbit, booster rockets are fired up to exert force on the satellite. This changes the speed and direction of the satellite. You may have questions about the validity of this law. This is not how things really work around you, is it? For example, if a batsman strikes a ball, the ball eventually comes to a stop, no matter how forcefully the batsman hits it. This has been explained through the concept of friction. Friction is a hidden force that arises between two surfaces in contact. This force acts in a direction opposite to the direction of the force trying to move an object. Friction is used in our daily lives to slow down and stop moving objects. To put it simply, the essence of the first law of motion is that all objects resist a change in their state of rest or of uniform motion. For example, when you try pushing a boulder at rest, it resists motion initially. However, if you exert enough force, the boulder starts rolling. Consider another situation where a truck is carrying an unfastened load. When brakes are applied suddenly, the truck stops, but the load moves forward and hits the back of the cabin. This is because the load tries to retain its state of motion. This tendency of undistributed objects to stay at rest or to keep moving at a constant velocity is called inertia. You can see this concept when you play a game of caroms. If a fast-moving striker hits a vertical stack of coins, sometimes only the bottommost coin in the stack is pushed out. The rest of the coins in the stack remain intact. The stack of the remaining coins comes down vertically, retaining their position of rest. This is because no force was applied directly on them. Now let's look at an object that retains its state of motion. A satellite orbiting the Earth continues to revolve with constant velocity, as no external force such as friction is applied on it. In real life, on Earth, it is difficult to find an ideal frictionless surface. Let's analyze some more cases where we observe this law at work in our everyday life. Look at the standing passenger in this bus. The bus starts suddenly and the passenger is pushed back. This happens because the lower part of the passenger's body, which is in contact with the bus, begins to move with the bus. However, the upper part of the body tends to maintain its state of rest. As a result, the upper body tends to fall backwards and the passenger experiences a jerk. Similarly, when the bus slows down by applying a sudden brake, a standing passenger tends to fall forward. This is because, at this time, the lower part of the body, which is in contact with the bus, tends to stop while the upper part of the body resists the change and tries to maintain its state of motion. Now that we know what inertia is, the next question is inertia equal for all objects? There isn't a yes or no answer to this question. Inertia is proportional to the mass of an object. This is evident when you try to push empty boxes versus boxes filled with packages. It is easier for you to push an empty box, right? Kicking a football around is fun. But would you try kicking large stones of the same size? No, that would hurt, as you can see. So, remember, the larger the mass of an object, the greater is the inertia. Based on this, if you compare a car and a train, and a plastic coin and a nickel coin, which of these would have more inertia? You would need to compare the mass of each set of objects. The mass of a train is more than the car, so the train will have more inertia. Similarly, the mass of a nickel coin is more than that of a plastic coin. Hence, the nickel coin will have more inertia. We are all advised to wear seat belts while driving. Why do you think it's so important? Let's find out. When the driver of a car applies brakes and the car slows down or comes to a halt, have you noticed that the driver's body tends to continue in the same motion due to inertia? Inertia is the reason the driver is pushed forward in such situations. The seat belt restrains the body and prevents this forward motion. By doing so, it protects the driver from injuries that may result on sudden braking at high speeds. In absence of seat belts, applying sudden brakes may cause the driver to hit the steering wheel or front panels of the car violently, resulting in an injury. As the first law of motion explains the concept of inertia, it is also known as the law of inertia. This brings us to the end of the lesson on the first law of motion. In this lesson, you have learned about Newton's first law of motion, inertia, and the link between mass and inertia. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. According to the law 42 of the laws of cricket, the bowling of fast, short-pitched balls is dangerous and unfair if they are likely to inflict physical injury on the striker, irrespective of the protective equipment he may be wearing. How could a small object like a ball inflict injury on a cricketer? The impact of a moving object differs based on its momentum, which is the product of the body's mass and velocity. A cricket bowling technique devised in the 1930s called body line involved aiming fast-paced balls at the shoulders of the batsman. In the past, many batsmen have been injured due to the impact of balls travelling with high momentum. In this lesson, you will learn about momentum and the second law of motion. At the end of this lesson, you will be able to identify the significance of momentum, state Newton's second law of motion, derive the expression for the measurement of force, and explain the impact of change in momentum in terms of impulse. To analyze the concept of momentum, let's compare the impact of moving objects in different situations. Observe the marble dropped onto the thin glass pane below. The glass pane is intact. But what happens if we drop a cricket ball onto this glass from the same height? Ouch! The glass pane shattered. Why did the glass pane shatter this time? What was different in the two situations? The height from which the marble and the ball were dropped was the same. So was the velocity of both the objects when they struck the pane. Clearly, it must be the bigger mass of the cricket ball that made a difference. As the mass of the cricket ball is more than that of the marble, its impact on the glass pane is higher than that of the marble, and thus it shattered the glass pane. Let's now look at another case where two identical marbles, say P and Q, are dropped onto a thin glass pane from different heights. First, we drop the marble P on a thin glass pane from a height of 1 meter. The marble P does not damage the glass pane. Now we drop another marble Q from a greater height. Wow! Dropped from a greater height, even this small marble has shattered the glass pane. Why was the glass pane shattered by the marble Q and not by the marble P, even though the mass of both the marbles is the same? As the height from which an object is dropped increases, the velocity with which it strikes the ground or any other reference level also increases. Being dropped from a greater height, the velocity at which the marble Q strikes the glass pane is greater than that of P. Hence, the impact of marble Q on the glass pane is greater than that of P. That's the reason marble Q shattered the glass pane while marble P did not have much impact on the glass pane. Based on these observations, we can say that the impact of any object on the other depends on two factors of the object causing the impact, namely, its mass and velocity. These two factors together constitute a physical quantity, called the momentum of a moving object. The momentum of an object is the product of its mass, m, and its velocity, v. It is denoted by the small letter p. Thus, you can express momentum as P is equal to mv. Momentum is a vector quantity. It is measured in kilogram meter per second or Newton second in the SI system and in gram centimeter per second or dyne second in the CGS system. Because of its momentum, a fast-paced cricket ball can hit and hurt the batsman or the wicket-keeper if the batsman is not able to play the ball properly. That's why batsmen on the cricket field wear protective helmets and body pads to prevent possible injury. Momentum helps us understand the impact of collisions and explosions. For example, it explains the impact of a collision between two trucks or a cannon firing. The greater the momentum of an object, the larger the impact is on the other object. Remember period films where we often saw columns of armies who used huge logs to break down the gates of a fort? The group of men holding the log goes back a fair distance from the gate. Then they run to the gate to ram the log into the gate for maximum impact. The velocity and the mass of the log together provide enough momentum to break the gates down. The momentum of this army column differs at different points in their run-up to the gate. Although the mass of the log is constant, their velocity is increasing constantly. That is, they are accelerating. Another example is when actors in movies perform stunts, such as breaking down a door. The momentum of an object increases when it accelerates. Therefore, the rate of change of momentum depends on the acceleration of the object. Newton's second law of motion states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. Let's verify this law using an example. Observe this billiard table. The yellow ball is at rest right now. However, when the cue ball hits the yellow ball, it is set into motion. After being hit, the cue ball moves with less velocity, while the yellow ball moves with more velocity. Thus, there is a change in velocity of both the balls, that is, a change in their momentum. Additionally, the direction of motion of the yellow ball is the same as the direction of motion of the cue ball. Now let's observe what happens when the cue hits the yellow ball with more force. As you can see, the yellow ball now moves a longer distance than the last time, before coming to rest again. Thus, when the force applied by the cue ball increases, the momentum of the ball increases as well. Hence, we can say that the rate of change in momentum of an object is proportional to the force applied on it. A lot of our actions are based on the second law of motion. Observe the cricket fielder reaching out to catch a fast-moving ball. As you can see, he pulls his hands back to catch the ball. Why does he do that? He does that to reduce the impact of the fast-moving ball on his hands, before bringing its velocity down to zero. By pulling his hand back, he increases the duration of time taken in bringing the velocity of the ball to zero. Newton's second law of motion can be expressed mathematically as F is equal to ma, where F is the force applied on a body, measured in Newton in the SI system and in dyne in the CGS system. M is the mass of the body, and A is the acceleration produced in the body. Let's derive this relationship using an example. Consider a ball of mass m having an initial velocity u. When a force of magnitude F is applied on the ball for time t, the ball moves ahead with an acceleration a. In the time period t, the ball accelerates to a final velocity v. Let p1 be the initial momentum and p2 be the final momentum of the ball. By the definition of momentum, p1 is equal to mu. p2 is equal to mv. Hence, the change in momentum is p2 minus p1 is equal to mv minus mu, or m multiplied by v minus u. The rate of change of momentum is the ratio of change in momentum to time. That is, m multiplied by v minus u divided by t. According to Newton's second law of motion, the rate of change of momentum is proportional to the force applied. This gives us the relationship F is proportional to m v minus u divided by t. The acceleration a of the ball is the ratio of change of velocity v minus u to time t. Hence, we can write this relationship as F is proportional to ma. We use a constant of proportionality k to equate this relationship. Therefore, F is equal to kma. In the SI system, a unit force is a force with a magnitude of 1 Newton. Unit force is defined as the force that produces unit acceleration, that is, 1 meter per second square, when applied on a body of unit mass 1 kilogram. Thus, substituting the values in the expression, F is equal to kma, and simplifying, we get the value of k as 1. Hence, we get the mathematical expression of the second law of motion as F is equal to ma. Therefore, according to second law of motion, you can express the force applied as the product of mass and acceleration of the body. Using the expression for second law of motion, we can define the relationship between the SI unit of force, Newton, and the CGS unit, dyne. Consider unit values for force, mass, and acceleration of an object, and substitute these values in expression F is equal to ma. You get 1 Newton is equal to 1 kilogram meter per second square. Since 1 kilogram equals 1000 gram and 1 meter equals 100 centimeter, 1 Newton is equal to 10 raised to the power 5 gram centimeter per second square. Since 1 dyne is equal to 1 gram centimeter per second square, 1 Newton is equal to 10 raised to the power 5 dyne. Let's again look at the second law of motion. According to this law, force equals rate of change in momentum. Rearranging the expression, change in momentum equals product of force and time. When a large amount of force acts on an object in a very short duration of time, it is termed as impulse. Here is an example of a situation where we see impulse at work. Consider a cricket ball bowled towards a batsman in a cricket field. The batsman strikes the ball with a large force that acts on the ball for a moment. The impact of the bat enables the ball to change its velocity in magnitude as well as direction. This is the impulse of the bat on the ball. Impulse is numerically equal to the change in momentum. Impulse is denoted by J and is measured as a product of force and time. As the impulse of a body is numerically equal to change in its momentum, the unit of impulse can also be expressed by the unit of momentum. Thus, the SI and CGS unit of impulse are Newton second and dyne second respectively. In karate, a man can break a brick with his bare hands, even though the mass of his hand is small. The high acceleration of the strike provides enough force of high magnitude to his hand to break the bricks. This large force acts on the brick for a short duration, making an impulse. This impulse helps to break the bricks. This brings us to the end of this lesson on momentum and the second law of motion. Hope this session provided you with an understanding of the concept of momentum and Newton's second law of motion. Now you can use the mathematical expression for force to solve problems in physics. The section on solved problems provides you an opportunity to review some model problems based on these concepts. To revisit the key points covered in this lesson, please review the flashcard at the end of this lesson. Why does the ball come back to you every time you kick it towards the wall? Looks like the wall is kicking it back to you, doesn't it? The speed of the return of the ball also differs based on the force of the kick aimed at the ball. Actually, the wall exerts a force on the ball to return it to you. This force is a reactive force and is induced by your action, that is, kicking the ball to the wall. What happens when you try pushing a wall? It pushes you back in reaction. Newton's third law relates the reactive force to the force applied on a body. In this lesson, you will learn about the third law of motion and conservation of momentum. At the end of this lesson, you will be able to state Newton's third law of motion, explain the law of conservation of linear momentum, and identify the situations where this law is observed in daily life. Newton's third law of motion, also known as the law of reactive forces, states, when one object exerts a force on another object, the second object instantaneously exerts a force back on the first. These two forces are always equal in magnitude but opposite in direction. These forces act on different objects but never on the same object. According to this law, if we push an object, it pushes us back. And if we pull it, it pulls back with a force of equal magnitude. Let's revisit the situations we observed at the beginning of this lesson. The boy kicks the ball to the wall, say, with a force of 10 Newton. The wall kicks the ball back with equal force. The direction of the force exerted by the wall is opposite to the direction of the boy's kick. One force acts on the wall, while the other force acts on the ball. In the second situation, the man pushes the wall with a force, say 100 Newton. What happens to the wall? The wall also pushes back with a force of equal magnitude. Both these forces act in directions opposite to each other. And one force acts on the wall while the other acts on the man. Let's verify this law using two spring balances, A and B. Spring balance A is fixed to a wall with the other end hooked to spring balance B, as shown. When a force is applied on spring balance B, it also stretches spring balance A. Observe the readings on both A and B. Both springs show equal expansion, indicating equal magnitude of force on the springs. The direction of expansion of spring in A is opposite to that in B. And as you pull B, its spring expands due to the applied force. Since A and B are hooked to each other, B exerts force on A, expanding the spring therein. You can say A is reacting to the pull force on B. Here, the force due to B is exerted on A, while the force due to A is exerted on B. To put it simply, the essence of the third law of motion is that every action has an equal and opposite reaction. Here, action and reaction refer to the applied force and the reactive force. This means action and reaction always occur in pairs. For instance, consider a boxer punching the sandbag. The sandbag seems to be punching the boxer back. Thus, force exerted by the boxer and the force with which the sandbag hits back form a pair. Let's examine some other situations where this law can be observed. If you push a spring fixed to a metal block with a force F, the spring pushes against your hand with same magnitude of force, that is, F. Let's now examine how this law applies in the case of a collision. Suppose two trucks, one big and another small, are involved in a front-rear collision. One would think only the small truck would suffer damage. However, that's not quite true. As you can see, the bigger truck also suffers damage. This is because when the bigger truck hits the small truck also hits back with a force of the same magnitude. Hence, there is damage to the bigger truck. The functioning of a lot of applications we use is based on Newton's third law of motion. Let's look at a few examples. Blow a balloon and release it without tying up the opening. The air inside the balloon escapes downward through its opening. The escaping air exerts pressure on the balloon, providing a thrust to the balloon and pushing it in the direction opposite to the direction of the escaping air. Here, the escaping of air can be regarded as the action. The motion of the balloon in the opposite direction is the reaction. Thus, the reactive force of the escaping air keeps the balloon afloat in the air till the air in the balloon is exhausted. Jet engines also work on a similar principle. A jet engine pushes air backwards during flight. As a reaction, the aircraft is pushed forward. If you like swimming and diving, you must be familiar with diving board. During a swimming event, a gymnast hops on the free end of the diving board before jumping off. The hopping action pushes the board down. When the board is released, it pushes the gymnast up in reaction. The reactive force enables the gymnast to jump higher. This shows that every action force is matched with the reaction force, which is equal in magnitude and opposite in direction. In the third law of motion, you see two equal forces acting simultaneously against each other on two objects when an event such as collision occurs. However, according to the second law of motion, the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction of the applied force. This means that during a collision, the rate of change of momentum of one object is related to that of the other, since the force exerted by both the objects is equal. However, the sum of the momentum of both the objects before and after the collision remains constant. Hence, in the absence of any external force, the total momentum of the system is conserved. This is known as the law of conservation of momentum. In this lesson, we will focus on linear momentum. Therefore, the law of conservation of momentum in this lesson actually refers to conservation of linear momentum. To understand this law, consider two spheres, A and B, of mass MA and MB, moving along a straight line. A is following B, and both these objects display unequal initial uniform velocities. Let these velocities be UA and UB respectively. The magnitude of velocity of A is greater than that of B. Momentum of an object is the product of its mass and velocity. Therefore, the momentum of each sphere is mass times its velocity. Assuming there are no external forces, the total momentum in the system will be equal to the sum of the momentum of both the spheres. Since the spheres are moving to unequal velocities along the same path, they will collide at some point. Let's assume that after collision, both the spheres A and B move with uniform velocities VA and VB respectively, in the same direction as that before collision. As the spheres move along a straight line before and after collision, their momentum is said to be linear momentum. We can use the second law of motion to find the relationship between the momentum of the spheres before and after the collision. According to the second law of motion, force is proportional to the rate of change of momentum. Upon collision, the force exerted by A on B, FAB, is equal to MB multiplied by VB minus UB divided by T. Similarly, the force exerted by B on A, FBA, is equal to MA multiplied by VA minus UA divided by T. According to Newton's third law of motion, these two forces are equal in magnitude and opposite in direction to each other. Here, FBA is the force of action while FAB is the reactive force or reaction. Since it is a reactive force, it is always indicated with a negative sign. By equating both these forces and simplifying the equation, the sum of the initial momentum of both the spheres before collision is equal to the sum of their final momentum after the collision. Hence, we can conclude that the total momentum in the system is conserved. You can observe the phenomenon of the conservation of linear momentum in a variety of everyday activities. For example, look at Jim getting off the boat. While jumping out of the boat onto the pier, Jim loses balance and falls into the water, as if someone pulled the boat back from under his feet. This is because when Jim exerts force to jump out of the boat onto the pier, he pushes the boat backward in reaction. Thus, you can see Newton's third law of motion at work. When Jim is in the boat, the total initial momentum of his body and the boat is zero. In jumping out of the boat, he exits that system using some momentum. Equal momentum is conveyed to the boat pushing it back. This is how Jim falls into water. Similarly, consider the example of a cannon. When a cannon is fired, the cannonball shoots off with a very high velocity. Since the force exerted by the cannon on the cannonball is equal to the force exerted by the cannonball on the cannon is pushed back in recoil. If the vanes of the cannon are not locked, the momentum due to recoil makes the cannon roll backwards. The law of conservation of momentum, formulated nearly 3 centuries ago, is an inference from a large number of observations and experiments. It is interesting to note that not a single situation observed so far contradicts this law. This brings us to the end of this lesson on the third law of motion. In this lesson, you have learned about Newton's third law of motion and the law of conservation of momentum. Let's quickly summarize the 3 laws of motion. The first law states that an object will remain at rest or continue to move at a constant speed in the same direction unless an external force acts upon it to change the state. Newton's first law of motion gives the concept of force. The second law states that the rate of change of momentum of an object is proportional to the applied force and takes place in the same direction as that of the applied force. Newton's second law of motion gives the measurement of force. The third law states that every action has an equal and opposite reaction. Newton's third law of motion gives the application of force.